Jimmy Wang of the College of Engineering is our fourth speaker, and his title is Building Bridges for Heat.
Hi, everyone. Let's start with doing a quick show of hands. How many of you here has been stuck in traffic right before you cross the bridge in Pittsburgh? Yes, there we go. I'm not surprised. At rush hour, thousands of cars funnel onto fuel bridges and everything bottlenecks. The same bottleneck problem is also happening inside data centers, except instead of cars, it's heat. In my research, built tiny copper bridges that help heat to move more freely from chip to the cooler. On the left side is what happens today. Inside a data center, the chips are generating an enormous amount of heat, and that heat needs to pass through one tiny layer before it gets to the cooler, the thermal interface. What is that? Think about pressing your two palms together. They might feel fully connected, but they're actually only touching at a few contact points. It's the same for a chip and the cooler. Between them are microscopic air gaps. And air is like removing all of the bridges. This matters because it prevents heat from taking the fastest route across. Heat travels mainly in two ways. One is like cars, it's fast and efficient, but only in metal, just like cars only drives on the road. The second is like us human. We can walk, climb, and even swim, but much slower. So when bridges are missing, the car stops, and the heat is forced to swim across the Pittsburgh River, which is much slower, and that creates a thermal traffic jam. So my research asks a simple question. What if we can build bridges right where heat needs to cross? And that's exactly what we did. In the middle is our solution. We grow millions of ultra-thin copper wires on the thousands of times thinner than human hair on both sides of a copper sheet. So when two rough surfaces are compressed together, these tiny wires will bend and reach into the gaps like a flexible forest. So instead of a few scattered contact points, we created thousands of continuous metallic connections for heat to pass through. Now you may wonder, what does this mean in practice? On the right side of the slide, you can see how fast data center energy use is growing, driven by AI. With our material, we can reduce the chip temperature by 3 degrees Celsius. This may sound like a small number, but in data centers, every degree matters. It allows the cooling components to run more efficiently, reducing electricity use for cooling by about 10%. Scaled across thousands of servers, the electricity we can save can power a city like Pittsburgh for an entire year. So, even though if my research happens at microscopic scale, the impact could be much bigger. Less energy wasted, lower strain on the environment, and a more sustainable future for all of us living in a world powered by AI. Thank you.